Welcome to Brain Vision.
In this question, we have two blocks of mass being connected together by a string. So on the left, we have a 20 kilogram mass, and on the right, we have a 30 kilogram mass that is connected to a spring. Now, this connection at this particular point at the start, this is unstretched, right? So it's in the equilibrium state. What happens now is that we pull this 20 kilogram by a distance of 20 cm. So this spring now becomes stretched, right? It's stretched upwards, and then we release it. So when we release it, what happens is that the block will go back down, it will compress the spring, and then it will go back up again to the uncompressed state and unstretched state before being stretched again. Right, so it's kind of like a simple harmonic motion going on over here, but we want to find at this point when it goes back to the equilibrium position, right, when it is unstretched, what is the velocity of our two masses? So why this particular point? Well, we are choosing this particular point because there is no elastic potential energy at this point. It is all just GPE and kinetic energy. Right, so just GPE and the kinetic energy exist at this unstretched point. Now, to make life much more convenient for all of us, we can set the gravitational potential energy at this point to be equals to 0. This is very much for convenience, and you'll see why later. So by energy conservation, we know that this final energy, this is our final energy, must be equals to the initial energy, right? Initial when after we just pull, just before we release this pulling. So at this initial stage, we'll have to find what is the gravitational potential energy at this stage, as well as the elastic potential energy, right? So at this stage, we have gravitational potential and elastic potential energy, right, at the initial time point. So what is the gravitational potential energy? Because we have set the unstretched state to be the 0 point or the reference point for gravitational potential energy, it means that the position, right, of the initial masses, the initial position of the masses is the reference point where gravitational potential energy is 0. So unstretched position is the reference position. For the 20 kilogram mass, it has gone below its reference point, so its gravitational potential energy is actually negative, right? When it has been put down by 20 centimeters, its gravitational potential energy is negative, while the 30 kilogram gravitational potential energy is positive. Right, so for the positive one, for 30 kilogram, this is mgh, right, where the h is 20 centimeters, so this is 0.2 meters. But for the 20 kilogram, it has moved downwards from its reference point, so it is a negative value, and we will get again mgh, so 29.81. But what is the h? Well, the h, the height, right, is the perpendicular distance, so we just have to take the angle over here, theta, take sine theta multiplied by 20 centimeters. So this 0.2 meters times sine 40 degrees. Right? We're given that the angle it makes is 40 degrees. Finally, we add the elastic potential energy. and that is given because it's stretched by 20 centimeters. So this half k, the spring constant, is given as 250 newtons per meter, and the distance that is stretched by is 0.2, so half kx squared over here. So evaluating this, we should get value of about 38.6 joules. And since we have previously set our gravitational potential energy at the reference point to be 0, which means that this must be just equals to the kinetic energy that we have. This is half mv squared, and we can find that quite easily. We can find the velocity by just taking 2 times the kinetic energy divided by 50, taking the square root of this, and we should get about 1.24 meters per second.